Today I'll talk about velocity profile and shear stress distribution in a horizontal circular pipe for laminar fluid flow. Last video I already found the velocity profile. Now here the velocity profile for laminar flow through a horizontal circular pipe uz of r, because here uz is function of r, is equal to minus 1 by 4 mu dp by dz r square minus small r square. So r square is the radius of the pipe, and small r you can vary from center line to the wall. So now if you reorganize, so minus 1 by 4 mu dp by dz r square, capital R square common, so that will be 1 minus r small r by capital R whole square. Now these show that velocity profile is parabolic. So now from here we can say that profile is parabolic profile. Now here if I put r is equal to 0, small r is equal to 0, so we'll get that r is equal to 0 means that is the center line or center of the pipe. So the velocity actually maximum. So Umax will be minus dp by dz r square by 4 mu. I always remember that center velocity is maximum. At the wall means r is equal to capital R, the velocity is 0, means no slip boundary condition. Now maximum velocity Umax we got occurs at the center of the pipe, so r is equal to 0, so that is Umax is equal to minus dp by dz capital R square by 4 mu, so that r is equal to 0. Now velocity profile we already got in the last video. So uz of r, so that is that minus 1 by 4 mu dp by dz r square 1 minus capital R by r square. Now this is nothing but that Umax, so we can write Umax 1 minus r by capital R whole square. So ultimately uz of r is nothing but Umax 1 minus small r square by capital R square. So now again the velocity profile. Okay, so already we know. So from this equation also, from this equation also we can tell that maximum velocity is at the center and zero velocity at the wall of the pipe. So here this equation, so this shows that velocity profile is parabolic with the velocity decreasing from the maximum at the center to 0 at the wall, means as here that the maximum velocity, if you go to that wall, so velocity actually decreasing, and at the wall velocity is 0, means no slip boundary condition is applied. Now we have that velocity profile. Now if I differentiate with respect to r, so du uz by r with respect to dr, when du uz by dr, so that will give dp by dz r by that 2 mu. So this we after differentiation we will get dp by dz r by 2 mu. Now shear stress we know that tau rz is nothing but mu minus duz r by dr. So now if we plug duz r by dr, so that will give minus dp by dz r by 2. So this is the shear stress formula, shear stress distribution formula. Now that we got that tau rz is nothing but minus dp by dz r by 2. So shear stress distribution formula. Now if I put the boundary condition at r is equal to 0, means here at the center line. So now if r is equal to 0 means the tau rz is equal to 0, means the shear stress varies linearly from the wall to the center of the pipe, but that here the velocity, that the shear stress is 0, means at the center velocity is maximum but shear stress is 0, means minimum, we can say that maximum velocity, minimum shear stress. Now at r is equal to capital R, velocity is 0 but that shear stress is maximum, so that if we put capital R here, r is equal to capital R, so tau max will be minus dp dz capital R by 2. So thus the shear stress is maximum at the wall of the pipe. So now we know what is the velocity profile and shear stress distribution inside the circular pipe. That's it. Thank you.